Welcome back to week 11 of the Fundamentals of Nano and Quantum Photonics course. And we are into the session 11 of this particular course. For today, my camera is not perfectly working and I don't have a separate device to turn on the camera. And so that's why I've turned it off. Uh, And today it's going to be a brief session and it's going to be different than the other sessions because I'm not quite occupied today due to traveling. I have to travel just tonight and maybe we will just try to analyze the questions which actually are discussed in this week. And there's a lot of material which basically is shared and you can watch the video lectures anytime. But I will be giving this particular lecture again, and we can discuss some of the topics briefly, particularly about the quantum nature of the light. And I'm Shazan Bhatt, and I'm a direct PhD student at IIT Bombay and TU Berlin. This course is being offered on NPTEL by Professor Naresh K. Imani. And we are into week 11, and as per the course outline, this is not exactly what the course outline matches. So today, what we are going to cover is basically, if you know, we are going to cover the quantum harmonic oscillator, quantum harmonic oscillator, and we are going to see about again we're going to see about something called as about the quadratures, about the light quadratures, what we basically talked about in the previous session. We're going to talk about the quantum nature of light. Again, we are going to talk it about in terms of the questions today, not this separate session. We are going to revise some of the previous material because most of it is based on the previous week. And these are the references in the books which you can follow. Particularly if you want to study basic quantum optics, you can go refer to this book by Mark Fox. And as per the ritual, this is a 2 hour session, so we usually take maybe 1 or 1.5 hours for the for revision. But today it is going to be directly solved or directly, uh, I should say, revised using the questions from week 11. So it's going to be maybe 1 or 1.5 hour session. And let's see what we can basically cover. So if you remember from the previous session, we talked about the phasor diagrams. If you remember the phasor diagrams, let me, we talked about the field quadratures. First of all, we talked about the field quadratures, wherein you define this x1 and x2, and this is basically x1 and this is basically x2 in terms of the sine omega t and the cos omega t function, and that those functions are related to q of t and p of t, and that q of t and p of t is basically related to the position and the momentum of the oscillator. When you go from a simple harmonic oscillator to a quantum harmonic oscillator, when you quantize it, then you still have these x and p, I should say, physical observables. But you write it in terms of q of t and you write it in terms of p of t, and you can relate them with each other. You can relate it with the x. You can write it something like this, and you can write the momentum something like the p of t is something like momentum divided by the square root of the mass. And then you can represent them in terms of the in terms of the field quadratures, where this is, let's say, x2, this is x1. And if you have, let's say, a circle centered at origin, then you call it as a vacuum state because there is no photon present. No photon. I shouldn't say no photon, but I should say it is a the if you solve the harmonic oscillator problem, you get E of n to be equivalent to h bar omega n plus 1/2, and n is exactly the photon number. If you put photon number to be equivalent to 0, you still get the energy is to be equivalent to h bar omega divided by 2, which is basically the energy of the vacuum fluctuation. So these are basically the vacuum fluctuations. So that's why it's centered around origin. That means these are I should say if this is x2, this is x1 uncertainty, then there is basically delta n delta phi uncertainty, which is greater or equivalent to 1 by 2. That means it's totally uncertain how many number of photons with what phase are basically present in case of a vacuum state. Now the question is whether you can squeeze it, whether you can just make it something like this, but centered around origin. In that case, you will be squeezing this thing and you will be expanding the other thing because of the uncertainty. Okay, now that is what maybe we are going to see in the questions. That is the first part. The second part is about the light as a quantum harmonic oscillator. Just like I discussed about this in the previous week, wherein you have the solutions of a quantum harmonic oscillator in terms of the legendary polynomials, or I should say legendary functions. When you solve the quantum harmonic oscillator problem, you go from a classical, let's say, classical oscillator model, which is a hanging pendulum. You go from a classical oscillator to something called as quantum harmonic oscillator, and you obtain the solutions which look something like this. This is n equals to 0, this is n equals to 1, this is n equals to 2, n equals to 3, so on and so forth. And then you call this E0 where there is no photon present, yet there is some energy present at that particular state, which is basically the vacuum state. Or this energy basically is called like quantum fluctuations, and it is the fluctuations in the field of a photon. That means even in vacuum, there is some probability of finding the photon, but that is very small. And you saw that how you can tune these vacuum fluctuations. You can basically tune them by changing the volume of a cell, the volume of a cell, or let's say a cavity in which the photon is present. So it's purely a photon cavity, I should say, interaction. Or you can even talk it in terms of the QED, something called as quantum electro, not a QED, I should say, something called as cavity QED. This company called as cavity quantum electrodynamics, wherein if you have a photon inside a cavity, then what is going to happen with that photon and how it behaves. So it's all of these are studied under cavity quantum electrodynamics. And how you can basically understand the effect of these vacuum fluctuations is basically you can go on, let's say, for example, if you have a quantum dot present in a cavity, you have a quantum dot present in this particular volume, then you have a quantum dot present in the other volume, then you know that the radiative decay, let's say if you talk about the radiative decay lifetime, let's say this is tau 1, this is tau 2, then you know that tau 1 will be uh, tau 2 will be greater than tau 1. Why? Because this will decay faster, so this will decay slower. Why it will decay faster and why it will decay slower? We talked about it, that this fast decay is due to because of I should say Purcell factor. You talked about the Purcell factor. What is the Purcell factor? It's how fast it decays inside a cavity to how fast it decays in a vacuum. And why this Purcell factor improves? And because of spontaneous emission becomes faster. And why does it become faster? Because of I should say the vacuum fluctuations, or vacuum fluctuations increase if you decrease the volume, if volume goes on reducing. So that is the factor you basically saw here, that the electric field, this is basically vacuum field. This is the vacuum electric field of what? Of a photon. So this vacuum electric field is inversely proportional to volume. So as you go on increasing the volume, these vacuum field reduces. And if you go on reducing the volume, the vacuum field increases. So that is the fundamental aspect of this particular, that's the fundamental notion of it. Then we talked about coherent and squeeze states. We talked about coherent states. These are the states which are similar to, I should say, classical coherent laser. Okay, so if you have a laser source, let's say this is a laser source, it's emitting some photons, it's emitting a beam of laser. So this light is basically this light is classical. Okay, so it's a classical but a coherent source. And but this laser source itself is quantum, because those photons are emitted, and The processes happening are basically via the quantum mechanics. The you solve the three-level system. The electron goes here, populates. Then this is a fast decay. Then electron populates this level. Then this is basically a transition wherein it emits the laser photons. It emits the photons which are basically coherent in phase. And but the nature here is basically that this coherent states are basically quantum analog of monochromatic wave. Monochromatic wave is this basically this wave. It's having a single frequency. Okay, and now if you have, let's say, a state, a photon state, which is coherent, what does it mean? It means that it obeys some sort of a Poissonian statistics. And you can basically show it that the number of photons is basically square root of the square root of n. And that is basically if you talk about if you draw these coherent states on a let's say for example this quadratures where you define the x1 and x2 quadratures. If you draw it on this, then you have something like, if you have this as x2 quadrature, this is x1 quadrature, then you can define coherent state something like this, where this is basically defining the alpha, where this alpha is basically equivalent to square root of n. Okay, so this is the mean photon number or the length of this particular phasor. And this particular thing is basically phase of it. So this is basically phase, but you have this as the phase uncertainty. So that is why there is this delta x2, there is this delta x1. Okay, and in this case, delta x1 is equivalent to delta x2 is equivalent to half, let's say. Then you have these delta x1 and delta x2 to be equal in case of the coherent source, let's say coherent source. But what happens if you go on, let's say for example, let me draw it on this. If you go on squeezing, let's say it in this direction, if you squeeze this particular in this direction, then what you have basically done is that you have now reduced the phase uncertainty. Okay, so I'm drawing the blue one here again. So I'm drawing the blue one. So now if your state looks like this, let's say this is a coherent was a coherent state. Now you have squeezed it here, but you have elongated it on the other end. Now by squeezing, what has happened is that the uncertainty in phase, which is basically this delta phi, has reduced. So uncertainty in phase has reduced, but as you see that the length of this phasor will become, I mean the length of this vector of this phasor, which is basically the mean photon number, that increases, because now earlier it was only up to this length. Now it is going up to here. It can be here, it can be here. So this part has elongated. That means the uncertainty in the photon number has increased, but the uncertainty in the phase has reduced. So that is how you play with these phases and what you call as amplitudes, because there is a amplitude phase uncertainty. I guess this is 1/4. And what does it mean now? Now it means that you can tune these particular states in order to play with the amplitudes, in order to have in order to, I should say, get the better out from it. Let's say, for example, if you want to have the phase information, then you are going to affect the amplitude information of it, and vice versa. And the application of these something called as squeezed states, that is what professor has talked about in the application of squeeze states part. I'm not going to go into that discussion. Maybe we can discuss it in the last session itself in the week 12. But that is what basically is basically discussed in these particular topics. Now you might have questions on this particular figure, wherein you are given a different types of these field quadratures shapes, and then you have to decide whether it is a, let's say, an amplitude squeeze state, whether it's a phase squeeze state, whether it's a coherent state, whether it is a vacuum state, whether it's a photon number state, photon number state. These are the possibilities which basically you have to talk about. So that is basically talked about in the first question itself. Now, then we again talked about here. Let's say this is what I was talking about, the coherent state, wherein this uncertainty in x1 and uncertainty in x2. And what are these uncertainties in x1 and x2? These are basically related to uncertainties in the position and uncertainties in the momentum itself. Okay, remember because x1 is related to x and x2 is related to momentum. If you see these equations, where are they? Not here. Yeah, if you see x1 and x2, they are related to q of t and p of t, and but q of t is related to position, p of t is related to momentum. So in a sense, then these basically uncertainties are related to uncertainties in the position and uncertainties in the momentum. And you know that uncertainty in let's say delta x delta p is basically greater or equal to h bar divided by 2. And this comes from the Heisenberg's uncertainty. And similar logic follows in these parts also. If you write it in terms of delta x1 and delta x2, you can write it in terms of delta x1, delta x2 is greater or equal to 1 by 4. But if you have a minimum uncertainty state, which is basically a coherent state, you have a minimum uncertainty state, that means delta x1, delta x2 is equivalent to 1 by 4. That means delta x1 is 1 by 2 and delta x2 is 1 by 2. And you know that the squeeze state is a way to go below the short noise limit. Short noise limit. So you remember that curve where the probability is where you have this as short noise limit, and you have this curve going down here, and then you said that you cannot detect basically below the short noise limit because it is limited by the instrument itself. But then the question is, how are we going to detect very few photons, let's say, very few photons? The answer to that problem is that you basically make something called as squeeze states. You go in the squeeze states regime so that you can basically go below this short noise limit. I don't know whether the professor has discussed about it, but that is the way how you detect very few photons. And particularly whenever you have very few photons, people deal with these squeeze states. How that is experimentally done, that is a different question altogether. How the phases and amplitudes of these particular few photons are basically played. So that is the fundamental aspect of it. And I wanted to show you one more thing. So yeah, okay. So let's talk about the questions now. If anything new exists, anything new we will encounter in the questions, then we can pretty much discuss about it. So the first question itself says that the phasor diagrams are a convenient way to represent the electromagnetic fields. So these are representing the electromagnetic fields, phasor diagrams, which are basically x1 of t, x2 of t, and this x1 of t is related to q of t, x2 of t is related to p of t, and this q of t is in turn related to the position, p of t is related to the momentum. Just remember, always remember this, and always think about it in terms of the position and the momentum, as if you're just drawing the position here, you're just drawing the momentum here. So it's almost like a momentum position, I should say, figure. Now, that is what the first question says. We have to answer the below questions. I think question 1, question 2, question 3, question 4, based on these figures. So now first, this x is x2 quadrature, this is x1 quadrature. Similarly for the other plots. Now you see for the first plot, you have a circle which is centered around some x1 and x2, and it's a perfect circle where this is basically the uncertainty in phase. If this is phi phase, then there is uncertainty in phase, which is delta phi, and then there is uncertainty in the amplitude also, which is delta n. Okay, and the length of this phasor is basically square root of n. Okay, so this is alpha, which is basically magnitude of alpha, and it's equivalent to square root of the n. And now similarly goes here. If you have this is delta phi, which is phase uncertainty, and similarly you have the amplitude uncertainty. And but here, if you see here, you have a perfect circle which is centered around the origin. You don't have any what you call as the shaded region. What does it mean? It basically represents something called as photon state, photon number state. It is almost as if I should say, you remember E of n you wrote as h bar omega n plus 1 by 2. It is as if this n is almost like it's actually a photon number. It's actually a photon number, but if you go into something called as Fock space representation, then this n basically acts like an operator, something called as number operator, and you can operate this number on a, let's say, some wave function, and you get some eigenvalue and you get some eigenvector, right? Such is the essence of this particular photon operator. So this is basically, it also acts like an operator. So it's something called as photon number operator. I don't want to go into the details, but this is basically how it looks like. So that's why it's just representing. You see that there is no shaded area. That there is only the length of this particular phasor, which basically represents square root of n, which is basically represents average number of the photons, average number of photons. So it's purely photon number state, and you don't talk about the phases here. You don't talk about the phase uncertainty here. Okay, and now, what are the other pictures? So this one I have been talking about. You have a perfect circular shape in a quadrature. You have a circular state that, and in this case, the delta. Let's say this is delta x2 and this is delta x1. Then delta x1 is equivalent to delta x2 because it's a circle, so it doesn't matter. It has a diameter which is same along the all sides. Just give me a moment. So, if you talk about, just give me a moment, I think. Hello. Okay. So, if we talk about these delta x1 and delta x2, these are equal. So, and this is a minimum uncertainty state. So, this is a coherent state basically. We have been talking about it. And if it's a coherent state, then it's a minimum uncertainty state where delta x1 delta x2 is equivalent to 1 by 2. Come on. Just give me a moment. Sorry for the interruptions. I'm receiving some calls, important calls. Sorry for the interruption. Actually, okay, that's fine. So this is a minimum uncertainty state. Now, what happens if you go on squeezing it in this direction? That means you have squeezed this particular in this particular direction, and you have elongated it in this particular direction. Now you see that this phasor, this vector, which is basically representing the photon number, average photon number, which is basically the square root of n, the uncertainty in it will go on increasing. Why? Because now that you see that this arrow will get elongated itself now. Okay, so this arrow it will get elongated, and as a result, just give me a moment. I don't know. So Okay, sorry for the interruption. I had some important calls to receive. So what we were talking about now, if you squeeze it in a single quadrature, one quadrature, you're going to make the uncertainty in other quadrature to increase. That means that now you have reduced the phase uncertainty, but you have increased the amplitude uncertainty because this arrow now the length of the this arrow uncertainty in the amplitude can go anywhere in this purple color lobe. So that means you have increased the delta n, and but you have reduced the delta phi. That means this is basically a phased phase squeeze state. Phase squeeze state. Why? Because you have reduced the this particular phase uncertainty, but you have increased the uncertainty in the amplitude of the photon number. And now this I talked about, this is basically purely a photon number state. Now what is this? The D part. If we talk about the D part, then this is almost the opposite of this, opposite of the B part. Now it is squeezed in the other direction, and due to that squeezing, you see that this uncertainty in the phase has gone on increasing. But because of it, now the arrow, which is basically black arrow, which is phasor, which is showing the photon number, average photon number, its uncertainty goes on reducing because now it's this particular state has been squeezed in this particular direction, and now the answer that means the uncertainty in the photon number has gone on reduced, and this arrow can point in a very small area of this circle now. That means the uncertainty in the photon number has gone reduced. If you have something like a state which is looks something like this, then it would mean almost the uncertainty in the, I should say, the amplitude is gone and completely vanished, but it's not possible because you would have a well-defined points in as kind of as the length of this phasor, which would be the average photon number, and the uncertainty, but there will be some uncertainty in phase, which will be huge. But it's not possible to make a state which is almost like a flat line because the minimum uncertainty you can have, which is delta x1 is minimum 1 by 2 and delta x2 is minimum 1 by 2. You cannot go below it unless and until you're not squeezing it, because once you are squeezing it, let's say you're squeezing this, then that means you are reducing delta n, but you are increasing the delta phi. And let's take an example. That means you are making delta n to be around maybe 1 by 4, but you are making delta phi to be greater than it, so that the product is basically the greater or equal to 1 by 4. Okay, so let's say for example this is maybe 1 by 6. So you're reducing it. That means you're increasing it. Maybe you are making it 1 over 1.5 or something. 1 by that is greater. Okay, this is going to increase. Okay, so that is the fundamental thing about it. Now this particular part, which is basically so this is basically amplitude squeeze state. So because you are squeezing the amplitude uncertainty in the amplitude, you're reducing the uncertainty in the amplitude. So this is an amplitude squeeze state. Now if we talk about part E, we have been talking about it. It's a circle centered around an origin where this is the uncertainty in delta x1, this is uncertainty in delta x2, and this is a vacuum state. Vacuum state. Why? Because you see that here the there is no length of the phasor. It's exactly centered around it. That there is the alpha, which is basically square root of n, is basically it almost tends to zero. I mean, it's negligible. So I should say it's e zero, which is equal to h bar omega divided by 2, where n is equivalent to zero. There are zero photons, but you have the field fluctuations. You have the field fluctuations, which is basically the vacuum field fluctuation. Vacuum field fluctuations, and because of it you can draw it in a you can draw its field quadratures, which basically will be centered around the origin with certain uncertainties in the quadratures, delta x1 and delta x2, but the photon number is zero. Average photon number is zero. Now that is very weird because you can have some photons popping in and out in a even in a vacuum state, because if there is a field existing, then you basically have certain photons popping in and out. That is basically what vacuum state means. So if you have this vacuum state, if you have this E0, the vacuum state, then you can have some photons, I should say something like popping in and out of existence, popping in and out of existence. And that is because of these fluctuations, which are basically quantum fluctuations. What are fluctuations? Fluctuation is something that is kind of randomly maybe oscillating, coming into existence and then going back. Those are basically the field fluctuations. Because if there is some kind of a field existing, then those photons are coming in, then they are going out, and these are very I should say minute fluctuations. That's why these are something called as quantum fluctuations. And as you even computed that the field of the vacuum field amplitude goes on increasing with reducing with the volume. So if you go on to a very smaller volume, maybe of the order of 2 nanometers or maybe 5 nanometers, then you see that the vacuum field amplitude goes on increasing. And you can even compute this vacuum field amplitude in terms of, let's say, volt per meter or something like that. And people are playing with these vacuum fields nowadays. And still people are trying to understand what basically is it. And uh, it's a pure notion or a topic of I should say understanding the fields and the quantum fields, quantum mesh I should say in this particular in the universe we are living in. And this particular now it looks like it's almost like a this is the state it was before, but now it has been squeezed in one of the quadratures. So it is squeezed in this quadrature. Okay, so it almost looks like this state, but a squeezed one. So almost like it looks like almost like a squeezed vacuum state if it's something like this exists. Let's see whether we have any question on this particular part. So now we have to answer these questions. The coherent state is represented by uh, so the coherent state we talked about, it's represented by A. It's represented by A. So the accepted answer, the correct answer is A, because delta x1 is equivalent to delta x2 is equivalent to 1/2. So it's a minimum uncertainty state. And okay. And why is it coherent? Because it follows the Poissonian statistics. Okay. Now the coherent state exhibits, that's what we have been talking about, even if you remember, even in when we talked about the second order correlation functions, we talked about this is a coherent state. But this is in terms of the second order correlation. This is time tau. And we also talked about the photon statistics. The photon statistics. But this is we're talking for classical coherent state. Coherent. Classical coherent light, I should say, not a state. Because if it is a state, then when we talk about state, we talk about quantum state. That is why coherent state is the analogous of monochromatic light. Whenever there's word state, it basically indicates a quantum state. Quantum state. So that means you're talking about some kind sort of I should say, few photons. And now you remember that even we talked about the photon statistics, wherein this was the probability of finding photon, and this was n. Now what happened is basically it exhibited a behavior something like this, which was almost like a not like this, I should say. It's not a Gaussian. It exhibited something like this, which is almost like a Poissonian distribution. You remember that particular curve wherein, if you have other questions, yeah, this one. So a Poissonian distribution. Each detector follows a Poissonian distribution with the average photon count. You remember these curves? So you have a probability of n versus n. So it follows a Poissonian distribution. These are the Poissonian distributions. Okay, and why this is discrete in nature. So because this is detecting a discrete photons now. We're talking about few photons. Okay, so now this is basically the photon number. So here it's detecting maybe 5 photons, 10 photons, 0 photon, 1 photon, 2 photon, but it follows a photon distribution. This photon distribution follows the Poissonian distribution. That's why I didn't make it a continuous distribution because it's not continuous. It is a discrete. It is discrete. It is discrete events because the photon detection itself is a discrete event. Okay, so that's why I hesitated in making it a continuous run here. So it's almost like something like this. Now the same analogy, if you have a quantum state of light, a quantum state which is exhibiting uh, which is a coherent state. A coherent state can be described something like this, where these uncertainties are equal and it's a minimum uncertainty state. Then it follows a Poissonian distribution, a Poissonian statistics. That means this delta n is equivalent to the uncertainty in the photon, I should say average photon number is basically equivalent to the square root of average photon number. So that means standard deviation is equivalent to square root of mean. It's basically standard deviation is equivalent to the square root of mean number of photons. So that is the characteristics of a Poissonian distribution. So the answer is this. Okay, moving on. The length of the phasor in the phasor diagram, which is gives the average number of the photons. So you're talking about these. Let's say this is a let's say talking about a coherent state, and this is a phasor. Then the length of this phasor, you talked about that this is represented as alpha, which is represented as square root of n. So this is the gives the average photon number. And what is it saying? It is proportional to square root of n. So that is what basically we're talking about. So this alpha, which is basically proportional to the square root of n, gives the average photon number. Now what? Now the phasor diagram that represents phase squeeze state. Now we're going to go back to this question where we have to show which represents the phase squeeze state. So we have marked it, the phase squeeze state is this. This is the amplitude squeeze state. So we defined it in the beginning. That means if you have something like if you have a quadrature which is x2, this is x1, and let's say this was a coherent state earlier, that means this is the phasor. This is let's say square root of n, and uncertainty in photon number is delta n. Then this is basically the phases, uncertainty in phases. This is delta phi. But what happens if you want to reduce the uncertainty in phases? Then you're going to make it something like this, so that you reduce the overall spread of these phases. So you reduce the uncertainty in phases. But what you are going to suffer, you're going to suffer with the photon number. So uncertainty in the photon number goes on increasing. So that is why this red is basically it is a phase squeezed state. You can play one at a time. You cannot play with both of these because of the uncertainty. Just like if you want to just like if you want to improve the uncertainty in the position, you have a trade-off that your uncertainty in the momentum will suffer. If your uncertainty in position reduces, your uncertainty in the momentum is going to increase. That is what basically this curve itself says. It is the uncertainty in the position and the even itself the momentum. And in what in basically the fields of that particular photon number. And and now what we are going to have is that means this is a phase squeeze state, which is a phase squeeze state B. Part B is the phase squeeze state. This is the phase squeeze state. Now, was there an if it asks which is the amplitude squeeze state, then we know that the part D, if you are asked about which is the amplitude squeezed state, then you have the part D as amplitude squeeze state, which is basically represented as this is x2, this is x1. So this is the coherent state. Then amplitude squeeze state will look something like this. Why? Because now you have the uncertainty in phase as delta phi has increased, but your uncertainty in the photon number has reduced. Okay, That means this uncertainty in photon number is basically the amplitude. Okay, that means that is why you present it as magnitude of alpha, magnitude of alpha, and this is something called as amplitude squeeze state. Remove this. Now consider the two statements mentioned below. The phasor diagram D represents the amplitude squeeze state. Yeah, this is correct. This is the amplitude squeeze state. Amplitude squeeze state presents an increased uncertainty in amplitude of quadratures. That's an increased uncertainty in delta n. No, this is absolutely wrong. Why? Because amplitude squeeze state represents a decrease. It represents a decrease in uncertainty, decrease in delta n. Okay, of the quadratures. That means it basically represents a decrease in uncertainty of the delta n. So the S2 is completely wrong, but S1 is fine. It's correct. That means the phasor diagram represents the amplitude squeeze state. This is an amplitude squeeze state. This one. So the answer is statement one is correct. Statement two is wrong. It's completely wrong. It's not even the reasoning of it. Okay, so give me a point. Now, just give me a moment. Okay, so the phasor plot C represents now, which is C. C is this one, and we talked about that it represents a number state, a photon number state, pure photon number state. You don't see a purplish highlighted region here. Okay, it's a pure photon number state. I talked about it in the discussion here, and now we have to match it. This is an interesting problem. Let me see other options. Vacuum state similar to phasor plot, phase squeeze state, physical quantum state plot to confuse students. Okay, so if we talk about the question 7 now, choose the correct option based on the table. It's a very good question, and it has to match the first one with the A, B, or C, and simultaneously with Roman 1, 2, and 3. Similarly, the second with A, B, and C, and simultaneously with Roman 1, 2, and 3. And there has to be only one option that is correct. Let's say, for example, if we just hide this answer right here, we are going to explain what is the answer of this question and how you are going to approach this problem. So first of all, you have to see what is amplitude squeeze state. Amplitude squeeze state, we saw that if you have a quadrature in the fields, if you have a coherent state, you start with the coherent state, let's say, and you have this as the amplitude of it. Then what you are going to do is that you are going to squeeze it like this, which will be basically an amplitude squeezed state. And that means your uncertainty in the delta n goes on reducing, and but the let me use this color. Uncertainty in the amplitude goes on reducing. This is basically amplitude uncertainty, and your uncertainty in the phase goes on increasing. But that means in doing so, you can once the uncertainty in the amplitude reduces, your delta n can go below the average photon number. That means because this uncertainty is reducing, that means the delta n can go below square root of average photon numbers. Once it does so, that means your delta n can become less than square root of n because you're reducing the uncertainty in the average photon number. So this is a possibility. That means it can go lower. But simultaneously, for the same state, your delta phi is going to increase. So you have to keep that in mind. That is one question, one part. Now, if you have a phase squeeze state, you have a x2, you have x1. Pardon me, this is basically x2. This is x1. Okay. Then what is going to happen if you start with some state, coherent state earlier? Then what is basically going to happen? What's going to happen is that you want to make you want to make it a phase squeeze state. So this is a phase squeeze state. So this is a phase squeezed state. That means the delta phi has reduced, but simultaneously the delta n increase. You see that this delta phi reduces. And now what has happened because of it? While doing so, because the photon number statistics is only defined in terms of delta n or the number of photons. So you have to see what is happening to the average number of photons. Uncertainty in the average number of photons here increases. That means your delta n can go above the square root of n value. That means your delta n can become greater than average photon number square root of average photon number. So that is a possibility. So you have two possibilities. If you have an amplitude squeeze state, your delta n can be less than square root of n. And if you have a phase squeeze state, your delta n can be greater than square root of mean photon number. And you know that if this is the case, if we talk about first case, then this is the first case, this is the second case. If we talk about first case, the delta n becomes less than square root of mean photon number. That means it becomes sub-Poissonian. It's almost like a sub-Poissonian distribution. And for this, it almost becomes a super-Poissonian distribution. Super-Poissonian. Remember the super-Poissonian, sub-Poissonian distributions? If it's a if it's a perfectly this is sub-Poissonian, sub-Poissonian, this is a Poissonian, and this is a super-Poissonian statistics, almost something similar to that. And that means if you have a amplitude squeezed, let me use the same color, amplitude squeezed, delta n can become less than square root of n. That means it can become sub-Poissonian. It can go into sub-Poissonian distribution. Similarly, for the photon, for the phase squeezed, your delta n can become greater than, and it goes into a super Poissonian distribution. The sub-Poissonian, the Poissonian one, it is automatically because earlier you started with the Poissonian. Earlier you remember you started with this black, which is basically a coherent state. So you started with a coherent state, and that was automatically itself having a Poissonian statistics, following the Poissonian statistics. So you only have two options. You can only either go to below Poissonian statistics, which is basically sub-Poissonian, and you can go above it, which is basically super Poissonian. So those are the only options which are available and which are possible. So the first one goes to B and goes to Roman 1. So 1 goes to B, goes to Roman 1, and 2 goes to C, goes to Roman 2. And this is the answer of this question. So it's a very interesting problem. You can basically have a look over it, and you can understand it very effectively. So now what? Now, okay. Now we're going to talk about the ladder diagram for the quantum harmonic oscillator. What is the ladder diagram? It's just a representation of if you just have a simple harmonic oscillator, you can go into a quantum harmonic oscillator. I'm not going to go into the details or the derivations of it again because the professor has done a good job in explaining it. Then you can discretize the energy levels. You get a discretized version of the simple harmonic oscillator, and uh, and you get these wave function values, which is basically psi n, psi of n minus 1, psi of n plus 1, psi of n plus 2, psi of n minus 2, and you can traverse this ladder of energies. You can go up, you can go down with the help of what you can do with the help of operators. What are those operators? Those are ladder operators. Ladder operators. And that is basically something called as creation and annihilation operators. Because you want to traverse this energy space now. And how you want to traverse, and how you can traverse it basically is using these quantum operators, which are creation and annihilation operators. So there are two types of these operators. One is basically something called as fermionic operator. The other is something called as bosonic operator, bosonic annihilation creation operator. Similarly for this annihilation creation operator. So this obviously applies for fermions, and this applies for the bosons having the integer spin. So these are having the half integer spin. So these are having the integer spin. Z plus means integer spin. Now, for example, how you want to understand it? I'll give you an example that if you have a, if you are operate if you have a, let's say, an energy level, you're talking about a, let's say, a quantum well, and you have let's say an infinite quantum well, and these are having some discretized energies. As you go up, this spacing between the energy increases, it goes on increasing. So let's say this is E1, E2, E3, E4. Similarly, this is for the conduction bands. This is above the conduction bands. So similarly for the holes, you have different energy levels. So this is E1 dash, E2 dash. What you're going to do is basically, if you want to understand what is happening to the electrons, or you want to theoretically analyze it, even if you want, let's say, for example, the electron goes from this to this, and one of the electron comes from the 4 to E. How you are going to do it is using creation and annihilation operators. So if you have some electron, let's say in state E1, and it goes to state, let's say, E4, what is basically happening is these states do not exist. I mean, these are the abstract ideas. What is basically existing is wave function, the shape of the wave function. That is what determines the state. Let's say in E1 the wave function is psi1, this is psi4. That means psi1 and psi4 would be having different shapes altogether, different distributions of the electrons. Those shapes determine the distribution of the electrons. Just like if you draw the distribution of electron, the quantum well, you draw it something like this in E1, then E2, then E3, similarly in E4, E4. Okay, so these are distributions of the electrons. Now, what is going to happen if you want to traverse this energy space? You can apply something called as, let's say, if your electron wants to go to E1 to E4, that means from psi1 to psi4 type of distribution. You can apply a creation operator, which is a dagger on, let's say, psi1, and you get some eigenvalue, which is basically an eigenvalue, and you get some state. Okay, so if you apply psi1 and you go to, let's say, for example, psi4, that means this increases by certain values. You cannot go exactly to psi4, obviously, my bad. So the creation operator can, okay, at one time make this jump to a single state. So it can go up by single state at a time. So if you want to go to E4, you have to apply the creation operator multiple times. That means you will apply, if you will apply a dagger to psi1, you will go to psi2 with some eigenvalues, which is basically the energy value. This is the energy value. Some, let's say, alpha. So alpha is the energy value. So this is the eigenstate. Okay. Then you will apply a dagger to psi2. Then you will get some beta, and you will go to psi3. Then you will apply a dagger again to psi3, and you will get some maybe gamma times psi4. So this is the operation you want to do. So this is how a creation and annihilation creation operator makes the transition, makes you traverse this particular energy space, but one ladder at a time. You cannot just apply a creation operator and for on psi1 and expect it to go to psi5. That's not how it happens. It just traverses the ladder, but one step at a time. Similarly, opposite is true for a annihilation operator. So if you apply a on a psi1, so it will give you 0. Why? Because there is no state below this. Okay, it's not going to go anywhere. We're not right now discussing. We're not talking about this particular space here. We are just discussing about the electrons, and but electron cannot go below this E1 energy. There is no state present below this E1. Later on, we will talk about what happens below E1 if we talk about vacuum states or something like that. But you cannot go below this. But if you apply, let's say, annihilation operator, let's say on psi 3, it's going to have some eigenvalue, and it's going to go to psi 2. So that is how it traverses this particular ladder. So now you have this particular ladder system wherein you can use creation and annihilation operator. And similar is the true for bosons. Let's say, for example, you talk about phonons. Then therein you talk about actually B dagger B. This is basically the phononic creation operator, and this is basically the phononic annihilation operator. Annihilation operator. What is this? It is basically a manifestation of the same phenomena. But because now you're talking about the phonons, you can traverse the phononic energy spaces as well. You can talk about the phonon energies, just like you remember, that if you have a fermion, then you can basically let's say, just write it like this. If you talk about the photons, you remember that you have the discretized energy as h bar omega n plus 1 by 2. So this n basically is a photon number, and this you can write in terms of a dagger a. So this a dagger a actually gives you a photon number. Applying the creation and annihilation, first annihilation operation and then creation operator basically gives you a photon number. So that this basically gives you some number. That happens similarly in case of I should say bosons, or if you have a phonons, and you can write the phonon energy, you can write its phonon energy space in terms of h bar omega b dagger b plus 1 by 2, and this b dagger will give you the phonon number. But the difference between the I should say, I think I should use B dagger B here also, because it's mostly used for bosons, and photon is also a boson. And the difference between the photon, the bosonic and fermionic is that if you have a fermion, then in a state it can only occupy 2 electrons max in a state with opposite spin. Uh, I mean, all of the quantum numbers cannot be same. N, L, M, S has to be different. If these are same, then S has to be different. It has to be plus 1 by 2 and minus 1 by 2. Okay, but what happens if you have a phonon, you can squeeze in a lot of bosons in a single state. What happens after that? That's a different problem altogether, but you can squeeze all of those bosons all together. And uh, they won't interact with each other because they are chargeless. But if you're talking about the fermions here, then fermions are charged, and you have a plus q charge, you have a plus q, you have a minus q charge on each of the, let's say, an electron. If we talk about the electron, bosons are chargeless. So all of those factors come into picture, and now what happens basically if you talk about this energy ladder here? If you talk about what's going to happen with this. Now, the first question here says, and this energy ladder concept and the quantum harmonic oscillator, it's a classical, I should say, it's a way to understand, let's say, what happens to the phonons phonons in a semiconductors. I'm just giving you a basic example, even though it's not basic to understand how the something called as electron phonon interaction takes place. Electron phonon interaction takes place in semiconductors, and it's a very hot topic, and it was hot topic, and it will always remain a hot topic because of the complexity involved. So the thing is that if you have atoms in a, let's say, a semiconductor, let's say silicon, or any of a semiconductor, and then you have electrons present here. And what's going to happen basically if these atoms come closer to each other, let's say these atoms came closer to each other, then the energy of the electrons goes on increasing. It has to increase its potential energy now to stay in the same vicinity of those two ions. So what's going to happen now is that these particular ions are going to come closer, and the electrons are going to uh, increase their potential energy. So that means if you have now, if you just squeeze this system, these come closer, then the electrons potential energy goes on increasing, How? Because of compressive forces. Now they have to spend more energy in staying at the same position. Okay, so that's the point. Just give me a moment. I'll be just back in a minute. Give me a moment. So what basically happens? Okay, so now if you have, let's say, now if you just expand this particular crystal, then electrons potential energy reduce, and you have a tensile because of the tensile forces. That means now you are varying the electron's energy. So this is basically something called as electron phonon interaction. So that means if you are somewhere applying the tensile forces or your compressive forces, you're going to change the electron's potential energy altogether, and that is going to have implications in your devices, in your optoelectronic devices, transistors, LEDs, lasers, all together. And you can induce these phonons, but you can study these electron phonon interactions with light-induced processes. Okay, so let's say you have a semiconductor, you can irradiate with some light source, and that will generate I should say, compressive or tensile forces inside the system, depending upon what sort of a light you use, what are the boundary conditions and other things. And then you can use another light source to probe it. It's something called as pump probe technique, and all of these processes happen in sub-picosecond time regime. So this is something called as femtosecond spectroscopy technique, and this is actually my research area. So you can study these processes in a femtosecond, which is 10 to the power minus 15 of a second. So all of these processes happen in that particular time regime. So you can see what is happening because of the phonon, how the phonons are getting generated, how the phonons are traversing this entire crystal, what is happening to the energy of the electrons, and that particular, I should say, interaction of the electron with the phonon, how the electron's energy is changing, and how that change in electron's energy is basically changing the dielectric response of this system. Optical response is changing. That means once the pump comes in, it excites the system, it excites the semiconductor system. Maybe it creates expansion. It creates, let's say, an expansion or compression, and what it does is that it changes the electron's energy. It changes the electron's energy. And what that does is basically it changes the dielectric response. It changes the dielectric response. And what it does, it changes the refractive index, refractive index for the probe, which is basically another beam of light coming through. And what it does, it can measure all of those major interactions, which is basically electrons energy. You can measure electron phonon interactions and all sort of other effects. I'm just telling you what basically happens and how why these all of these phenomena are important. Okay, so now you are given this energy space, and you have to traverse this particular space, and you are giving certain transitions. Let's say transition A, transition B, C, D, E, and F. You have to see what is going to happen, how you're going to traverse this particular space. Now, if you see that a transition is possible if you apply, let's say, creation operator over, let's say, a psi of n minus 2, then you are going to get some eigenvalue, and you are going to go to psi of n minus 1. Okay, that is the A operation. And the here you have to choose the correct pairs of transition subjected to operation A dagger 2. So you are applying A dagger 2. That means you are applying creation operator two times. Okay. So if you apply a creation operator two times, you're going to go to the above state, which is twice above in higher in energy. And which one is going twice higher in energy? So this is A is going once, B is going twice, C is going thrice up. So this is not. So these are coming down. So these are D, E, and F are not possible because we are talking about creation operators here. So the only logical option which basically seems to be logical is B. Why? Because in B, B is going from psi of n minus 1 to psi of n plus 1. And that is only possible if we apply a creation operator on psi of n minus 1. You go to you have some eigenvalue and you go to psi of n, then you apply a dagger on psi of n, you go to you have some eigenvalue and you have some psi of n plus 1. So this is the operation. This is what basically a dagger two times have been applied on this particular system. Now I wanted to explain what basically these operators are in terms of the matrix, but I won't go into that particular detail. It actually looks like it actually looks like a matrix which looks something like 0 square root of 1, 0 0 0 0 square 2, 0 0 0 0 square root of 3, so on and so forth. And that is how you basically do calculations with these. When you do the simulations, you do the calculation in terms of the matrix. If you are aware with the MATLAB, and MATLAB is comfortable in using the matrices. It basically is matrix laboratory, and these annihilation creation operators are basically represented in terms of these matrices. And where does this come from? This comes from a simple fact that this is basically almost like a square root of n plus 1. So if you apply this operator on any wave function, let's say psi, then you're going to get square root of n plus 1, psi plus 1. So if you now have n equals to let's say for example you have n equals to 2, you have square root of 2, n equals to 3, you have square root of 3, n equals to 0, you have square root of 1. Okay, so on and so forth. And that is basically the representation of it in a matrix form, but I don't want to go into the detail. We can have a separate session on it. But the simulation of it is more interesting, to be honest. If you want to understand the quantum system, just go and simulate it using the matrix notations and see what basically what are the results you obtain. These are quite interesting and fascinating results. Now, uh, which choose the correct pair of transitions subjected to operation A. So you have a applied now an annihilation operator on a quantum state, and that's going to bring it down. So which are the transitions that are going down? The D, E, and F. All of these transitions are going down to the correct pair of subjected to operation A dagger. Operation A dagger means you have applied it the A dagger once only. That means you will go from higher state to lower state only a single transition will take place. So this is the correct option. So this is the correct option. For F, basically it goes here, then it goes back to here. So for F, it is basically A two times, applying A two times. That means it's subjected to A hat because it's an operator two times. That means the annihilation operator two times. For the D, it has gone from psi of n plus 2. That means psi of n plus 2 to psi of n plus 1. But you have applied the annihilation operator with some eigenvalue you got. So the only logical operation is D and E. That's basically the answer of this question. Okay, so the commutator of the two quantum mechanical, or just give me a moment. Let me just back in a moment. Okay, so we're into the final question. Now we're talking about the commutators. You have Professor might have talked about what is a commutator. So if you have a commutator of two operators, then you can basically present it as A dot B minus B dot A, and if two operators commute, then they have the same set of I should say eigenvalues. Let's say if you talk about x and p, these x the position and the momentum operator doesn't commute. So you get something like I h bar. That means x dot p minus p dot x is basically I times h bar. So similarly, you have other quantum mechanical operators where you can find the commutation. It comes if you have the prerequisite of this course is basically quantum mechanics, basic quantum mechanics, and therein you discuss these commutators in details. So the accepted answer is basically AB minus B of BA. So this is the acceptable answer of this question. And what is the physical interpretation of this commutator of two quantum mechanical operators? You can just open any book and you can just maybe just open Griffiths and you can understand what basically it means for two operators to commute. Whether it's operators means it can be, let's say, a position momentum, it can be an energy operator also. You have the physical observables. When we talk about the physical observables, and these are the quantities which we can measure actually. These are position operator, momentum operator, energy operator. These are the actual operators. And this position moment the position operator is as such a position, and the momentum operators can be written as dou over dou x, dou over dou over dou y, I h bar, dou over dou z. Okay, and the energy operator is basically minus h bar square by 2m dou square divided by dou x square. So this is the energy operator. So these operators are just like, I should say, these operate on some wave functions. They itself don't have any meaning if you don't have a wave function to apply for. Unless and until you don't have a psi here, any state, then they apply on that state. Otherwise, these are just like certain quantities. Okay, and these are not, pardon me, the physical observables are the position, momentum, and the energy, but these are the operators corresponding to those physical observables. So these are the operators uh, corresponding to physical observables. Okay, and this comes from basically from I talked about this comes from first quantization. Okay, when you quantize it using the Schrodinger equation and you quantize the physical observables, that is the first quantization. If you talk about second quantization, that is basically field quantization. Field quantization. And that is where you get basically those notations of A dagger, A, B dagger, B, because now you're talking about quantizing the fields. There's like a photon field, which is basically an electromagnetic wave, just like a phonon field, which is basically an acoustic wave, just like a magnon field, magnon, this is basically a spin wave, and so on and so forth. So these are directly obtained from the field quantization. So these are actually fields which have been quantized using second quantization picture, and you get those annihilation creation operators. That's the notion I have been actually talking about from the beginning. So that's it about the lecture for today. I think we spent almost 1 hour, some 20 or 30 minutes on it. And now what we are going to see, we're going into the final session of the week 12. That will be on, I guess, that'll be on maybe 7th of October, I guess. Yeah, it's 7th October. 7th October. That will be Tuesday, and that will be from the Indian Standard Time, 11:30 a.m. to 1:30 a.m. Sorry, p.m. And we are going to finish it with the resonant light atom interactions, time-dependent Schrodinger equation. That is extremely essential to understand the time-dependent processes. I mean, till date, you have been only solving the time-independent Schrodinger equation. Just like if you have an electron in a quantum well, you solved the something like minus h bar square by 2m dou square psi over dou x square in one dimension. plus E plus some potential times psi equals to E psi. You consider the potential, let's say, to be equivalent to 0. So you solve this particular problem. Or even you solve something like dou square psi over, if you rearrange the Schrodinger equation, you get something like you get something like minus twice m divided by h bar square, v minus e of psi equals to 0. This is what you solve till date, time independent Schrodinger equation. What happens if you solve a time dependent part also, which is basically I h bar dou psi over dou t is equivalent to e of psi. It's basically h of psi, which is a Hamiltonian. So this is the time dependent Schrodinger equation part. And if you solve this, you get a psi of t to be approximately e to the power I omega t. It's almost like a oscillating part, which is time dependent. And this omega is basically h, which is Hamiltonian. It's an operator also. It's the total energy of the system divided by h bar. And you can write psi of t now as e to the power I h t over h bar. And now this h is a Hamiltonian. And now Hamiltonian can be written in terms of a matrix. So this is basically then a matrix exponential. And how you solve a matrix exponential, that's a different story altogether. You can write it in terms of a series of exponential. E to the power x can be written as 1 plus x squared divided by 2 factorial plus x cubed divided by 3 factorial, so on and so forth. So you can expand it. You can do some sort of tricks if you have a Hermitian matrix. If you have even if you have a purely diagonal matrix, then it becomes easy. If you have e to the power some a b 0 0, then you can write it some e to the power a plus maybe e to the power b. You can do all of these basically tricks, and this is basically the time dependent part. And this time dependent part is essential in order to understand electron dynamics or even photon dynamics. Even if you can understand phonon dynamics, all of those dynamics, which is basically a time dependent process, can be understood by solving the time dependent Schrodinger equation. Essentially, all of those processes are time dependent. Okay, and in order to understand that, you have to solve these time dependent equations. And the I should say the higher version of it, when you solve the something called as Schrodinger equation, you go into a time-dependent Schrodinger equation. Then you have something called as, just like you have a rate equation, which is dn by dt is equivalent to some some sort of a. You remember the if you have an electron in a device, you wrote the rate equation. Some electron in some semiconductor, you wrote the rate equation as dn by dt, which is equivalent to some factor here, d square n by dx square plus some generation term minus some recombination term. Remember this rate equation? Okay, so it's a time dependent equation, and you considered in a steady state this dn by dt is equivalent to 0. That means there is no significant variation with respect to time. Then you solve this steady state equation, which is d square n by dx square plus generation minus recombination equals to 0. So this is the equation you have been solving. Similarly, this is a classical rate equation. If you want to solve a quantum mechanical rate equation, you have to solve something called as density matrix equation. That it's almost like a rate equation, but instead you have something like dn by dt, which is equivalent to dependent on Hamiltonian. There is some term like I h bar and what am I missing? Yeah. So there is some term like IH bar, and then there is Hamiltonian, and then there is some density. Maybe you can write it as in rho. So this is something called as density matrix formalism. It's a rate equation, but it's in terms of a density matrix, which is rho is basically a density matrix. It's a quantum mechanical analog of this particular rate equation. And there are some scattering terms, some dissipation terms, but this is a quantum mechanical process. And it takes into consideration electron-electron interaction, electron-phonon interaction, maybe some all other interactions which you can consider at a at atomic level. Okay, and then you have to solve this rate equation. It's sometimes called as von Neumann equation also, and it's a quite a interesting I should say field to understand these time dependent processes. But I don't think we are going to go into a density matrix formalism or master equation, any sort of thing. So uh, we are going to see the basic time dependent. I just wanted to give you a flavor that how you can basically understand. And this density matrix, even you can you can write it in terms of maybe some A dagger A type of formalism. Basically, that gives you the density. Okay, that gives you the number. That's what I was talking about. So if you have a row, if you can write row as A dagger A, so you're basically seeing the evolution of the number. So this is a number. This is a number. So you are seeing the evolution of a number. A dagger is an operator. So you're seeing the evolution of that operator. And then this term comes into picture. Then you have to consider something like memory system with a memory and a memoryless system, something called a Markovian process. I don't want to just throw the jargons, but if you understand that this is the how you go from a you have been studying the classical rate equation, then you go into a quantum mechanical rate equation, which is almost like a density matrix evolution, the evolution of the time evolution of this number operator, which is basically a or a operator, and then you have to solve the density matrix equation. It's basically something called as von Neumann equation, and then you can actually see what is happening or what is going to happen with the electrons in time. That is basically the essence of this particular equation. And then there are other yeah, there are other ways to solve it. Let's say something called as time-dependent Green's function, or let's say something called as non-equilibrium Green's function. It's a very cool way to do the time-dependent problems. If you remember, I told you that if you have a let's say a device, this is a source, this is a drain, and if you have a single electron or a single atom system moving between the source and drain, then you can write basically a Hamiltonian of this system, which is a matrix. Okay, and using this Hamiltonian, you can compute something called as Green's function. Green's function. You can write Green's function as something like energy times identity matrix minus h sigma 1 sigma 2, where sigma 1 is the contribution of because of this, sigma 2 is the contribution. These are like self energies because of the source and the drain. Okay, so these are like energy contributions from the source and the drain to this electron. This you have to take the inverse, you get the Green's function. If you get the Green's function, you can get something called a spectral function. What is this? I don't want to go into detail, but if you know spectral function, you can obtain the something called as density of states, which is basically the spectral function divided by maybe 2 pi, something like that. If you know density of states, you can know the concentration, which you can get as density of states times the Fermi function, and you can integrate it in order to get the number. This is basically n as a function of E, and you can integrate the density of function with some energy E1 to E2, and you get n, which is a number. If you know n, then you are pretty much good to compute current, because current is some nq times mobility times electric field, provided you are applying certain some sort of a field. And if you know current, you can obtain current voltage characteristics. You can obtain all of the exotic things you are doing in the device. So this is the way of how you basically go from a quantum. This is a quantum. This is quantum density of states. Then you enter into a almost semi-classical. Then you enter into a current voltage characteristics. That is you. That's how you go from a quantum to classical, and that is how you do the calculations classically. So this is a topic of something called as quantum transport. But I'm just giving you a flavor of what basically is taught in the courses and how it relates to all of these. It's almost like a amalgamation of all of these things. Okay, so I think we should wrap up for today, and we will meet again in the final week. And thank you guys for patiently listening. See you next time. Bye bye.